Hi, Professor. My name is Nar Sheklin. I'm from Group 15 of Logic Design. We are assigned with problem set C for assignment 3, which is constructing a milli-state machine that will detect the sequence bit pattern of 0, 0, 1, 1, 0. And by the way, I'm sorry that I need to record the screen of my laptop with my phone because the Quartus program won't allow me to screen recording the code and everything, so I need to do this way instead. So first of all, these two lines are a matter of importing the libraries or the standard logic library. This block here is defining the entities. I define it as AS3, which stand for assignment 3, and all the variables, all the inputs, which are clock, resets, and the input W, and the output is C, which is the output, ending the declaration of variable. And this is the architecture and behavior of these entities, which is defining custom enumerated data type for the state for the machine states, and also declaring the signals to hold the current and the next state. And let's begin the process. The first process is you need to understand first that the first process is defining the first state as state S0, which is the initial state to wait for the first input bit for the first zero, the first significant input bit, which is the 0 in this sequence bit pattern. And then if the reset n equal to 0, it is an asynchronous reset. If the reset is 0, it will reset the FSM to the initial state as 0. Otherwise, on the rising edge of the clock, it will update the current state with the next state. Let's begin the process for the next state logic and output logic in the machine. Let's begin with assigning the output with 0 with no detection, and let's identify each case whether the state gonna change or not depending on the input. If the input is 0 and the current state is S0, it will change to the next state it will change to the next state, which is S1. Otherwise, it will stay at the same state, S0. Then at the state S1, if the input detected is 1, it will go to the next state, which is S2. Otherwise, it will stay at the state S1, the same. If at the state S2, if the detected input is 1, it will go to the state S3. Otherwise, it will go back to the state S1. At the state S3, if the detected input is 0, it will go back to the state S1 and giving out the output of 1. So this value of C will become 1 in this case. Otherwise, it will go back to the state S0, or the sequence is broken to the reset state, ending the condition. And this is just for the fallback case and safety case. And this is the test bench. As you can see, we assign the clock value to be fluctuating from 0 and 1, which with the waiting time of 10 nanosecond each. So the total period of one period of clock is 20 nanosecond. And these are all the test bed we created here. And let's see the simulation. I already turned on the simulation in the model simulation. Sorry. As you can see here, this is the first line is the clock, the second line is the reset, the third line is the input, and the fourth line is the output. As you can see, the output is 0 all the way except for here, because let's take a look at each rising edge clock that are nearby. At this rising edge clock, this one rising edge, it will equal to the input of 0, and then at this clock period, it will match the input of 1. At this rising edge, it will match the input of 1, and at this rising edge, it will match the input of 0. So now the sequence is detected and the output will become 1. So and as no other input is detected, again it will remain 0. And this is our state diagram and state table. Okay, thank you very much for watching this video. Have a nice day.